Now, once we have looked at this entire detailed analysis of torsion using Prandtl's theory and Prandtl's stress function, the last two closing points in this chapter are about, one is Saint-Venant warping function, right? And the second is membrane analogy, which subsequently builds into strip or thin sheet torsion problem. Now, the theoretical framework which we discussed in detail was very helpful to understand us what happens to this as a cross section when you twist it with a couple, right? We looked at how the formulations were done, how the formation of theoretical background was done, how the stress strain behaviors were done. We looked at a square cross section as a particular example, right? In further to this, we always looked at here that warping is function of xy and d theta by dz is equal to constant are two very peculiar interests and properties of this theory, right? The Prandtl stress theory. Once this framework is done, Saint-Venant actually came up with warping function discussion in detail. What is this warping? What happens when you look at this section? Say for example, this is a cross section of a bar, a thin bar. What happens to it? It would behave something like this, the section. So it has come out and warped and has twisted. So visualizing that and understanding the mathematical foundations of it is what Saint-Venant's principle help us to do with. And the reason of why it is important is the following. In aircraft, if you look at your wing, right, it is a thin structure, right? So that thin structure is going to have some warping, some twist. So torsion analysis is useful. So we will look at what is this principle, and then we will also look at a very, very excellent analogy, which is membrane analogy. Again, this was done by Prandtl, and let us reconfirm that because this is a GATE examination question, right? So Prandtl and his colleague. So it is called Prandtl's, but it is Prandtl and his colleague, right? So it is his analogy that if you look at a membrane which is squeezed and which warps out, twists to resist that load, the problem of torsion and membrane are mathematically or physics statistic wise equivalent. The phenomena governing is slightly different, but the formation of the problem, the setup of the problem is such that the analogies are identical, and it simplifies your task to solve these equations much in detail. So after looking at this, then we will quickly look at what happens to thin shaped torsion problem, a strip problem based on this formation, and then close the theoretical and mathematical foundations of this chapter. So let us start one by one. We will look at first Saint-Venant's warping function. Now to look at this, what we have to do is we have to visit back our theoretical framework that we looked at, right? So what we said is u is minus of theta y and v as theta x, the two-dimensional displacement fields. Now we have already done a very good argument from an induction principle, the physics principle, that why warping is independent of z and only a function of xy. Now another thing is warping is because of the twist of each cross section, right? This disk is going to move and therefore some part of it is going to come out. So intuitively what Saint-Venant said is this warping is proportional as this, and he defined this as d theta by dz. Remember, d theta by dz is constant because we said the twist is a linear variation, so it is constant. So the constant of proportionality he proposed for warping is the same as the rate of twist, and he gave a very beautiful argument by starting with a very simple square structure. If you look at this square, when it warps, the twist gives a projection, right? And the rate of twist is what gives that projection angle. So if this slice is going to move by 30 degree, the slice next to it is by 31 degree, the projection of this line is through that d theta by dz, which is 1 degree, which is protruding out that particular section for a given xy coordinate. So what he said is, extending this analogy to any general arbitrary surface, is that one particular point, the line of that warp, because for given x and y across z, which is a line like this, all the points will have this gradient d theta by dz in the twist out of plane that they come. And so because of this d theta by dz, the projection which will come out is going to be same as this constant. And this is a very, very powerful argument, because it is going to solve our life very, very clearly and beautifully. So once this W is done, now we will look at our strains, right? This is also known. This automatically gets satisfied, right? Because you don't have to do anything. The formation is such that it is this. Now, gamma Zx is del W by del x plus del U by del z, right? And del U by del z, as we know clearly, is nothing but minus of y d theta by dz. And del W by del z here is nothing but d theta by dz del psi, right? Because it is with respect to this, so del psi by del x. So d theta by dz can be brought out, and you have this del psi by del x minus y, right? Similarly, gamma yz, which is the other remaining component of the strain, is d theta by dz del psi by del y plus x, right? Same analogy. So in terms of warping function, you have got these outcomes. Now again, you can also show based on this that this satisfies this. All that these arguments are very clear to us, and these strains are related to stress simply using, I multiply it with G on both the sides, and what I am left with is this, correct? Now, this is a beautiful analogy. At this point, I would like to draw your attention to this important result of equation of equilibrium, which we satisfied with these, right? So, I would like to call back your attention to this exercise we did, sigma x L m, where I said L tau xy m plus tau zx n, right? Then I moved these constants here, m, n, l, n, l, m, right? So things move out. So n comes here, l goes out, right? The angles. So it is a diagonal matrix. This we said is automatically getting satisfied because nth component projection is anyway 0, right? This is cancelled out. Sigma z being 0 goes out. Here only thing, so this L and M analogies are left. And since these are directional constants, what we said further is from the equation of equilibrium of x bar, del tau zx, right, by del x, because this is by del x, plus del tau zy by del y, del sigma z by del z. This is anyway 0. In absence of body force, the equilibrium equation is this. Now, if we differentiate this further, g, d theta by dz is going to be invariant, right? It's almost a constant. Since x and y will get eliminated, so we have come up at an extremely important result, that this Saint-Venant's warping function satisfies the condition del square psi equal to 0. Poisson's equation, fantastic, because my life has become extremely simple. Then this equation, if I substitute these, right? If I substitute these, what I am left with? I am left with del psi by del y plus x, which is this component, into m plus del psi by del x minus y into L is equal to 0. I am using the second equation of equilibrium from here. apart in addition to, of course, the equation which we looked at, which is this, correct? So effectively I am saying that these equilibrium equations provide me a similar analogy as the Prandtl stress function. Now you can show easily that this also satisfies your stress, but that is not a part of any GATE or standard examinations. Most important is, so far we have not used in this framework what is called as torque balance, right? Because we have said what you have is tau zy x minus tau zxy integral dx dy has to balance the inbuilt torque, right? We looked at this twisting argument over the surface. The integral of this has to resist the total torque. If I now substitute these parameters from here, what I am left with is g d theta by dz, which is constant, which is going to come out, del psi by del x into x dx dy, right? And similarly, the right? This is what I am going to be left with after substitution. So G, and this is G J theta dash. We have already started expressing our torque as G J theta dash, right? So by comparing this, you can see that J is nothing but this double integral of this. So if you know J already for a section, you know this constant of integration, and then you know that del psi by del y, right, minus del psi, so this is x into this, del y into y, right, plus x square minus minus, so x square plus y square dx dy is going to be g. So based on this, I get the first moment. So warping function reduces to torsion problem in determining this, which satisfies these two conditions. So it has to satisfy this, which means it is a harmonic series, and then it has to satisfy this, right, which continues. So based on this, Saint Vincent said that my warping function is so easy to be determined, as similar to stress, that W is easy to be understood based on this. So this is a theoretical framework. We will park our thoughts here. We will now go to membrane analogy, which is equivalently important, and we will keep our thinking closed here before we go back again and revisit to solve one particular case of Saint Vincent's warping function. So the next part in our laundry list is to look at membrane analogy. Right? Now, for membrane analogy, what we have to look at is we have to think about a membrane. Right? So imagine this is a membrane. This is a small section of it, right? Subsection, which is what you are looking. And in this axis, so this is xy axis, right? And the z axis here, if you see, membrane looks something like this, right? These are the normal reactions, and then these are the loads, Q, per unit load, right? So what we are saying is, imagine this is a membrane. Let us actually draw a curvature shape of this membrane, which is in this x, y, z shape, right? So imagine this membrane here, right? What I am doing is I am applying a uniform load from the bottom to it, right? So this is all uniform load from the bottom, which is trying to expand this membrane, which is getting balanced by these normal reactions across, right? And from this direction as well. These are the surface normals at the surface, and these are the reactions, okay? And this is getting in such a way that, see, because n has to offset the projection of component of this cube such that the load Q, which is per unit area distributed load uniformly, is offset and balanced by this. Now, in membrane analogy, the vertical, this displacement in Z is W. We don't know whether it is warping, but it is simply the elongation in third direction to enable resisting of this load. But we know that this Z, the membrane which goes up or down, this pinch, the bulge in the Z direction is going to be function of xy. It may not always be uniform and constant. It may be a function of xy, which means over this edge, if I look, this angle is nothing but del W by del X. If the membrane was initially flat, this edge lifts up by something, the angle that it forms when it becomes infinitesimally small displacements is del W by del X. This W is a function of X. So at this point it is del W by del X plus del of del X of del W by del X into delta X, because this entire length is delta X. So the gradient, rate of change of del W by del X, right, is what this angle is between the two. And now therefore in x-axis direction, if I start writing the equations of equilibrium, what I am going to see is n delta x del W by del X del square W by del X square into delta X, because this is what it is, plus del W by del X minus n into del W by del X into delta X, right? Because that is what is this total load condition. So if this is delta X and this is delta Y, and delta Y is the total load per sheet, and this is the one variation over X, which means actually this factor can go out. This is the contribution of these loads which are acting along this surface, right? Delta X, delta Y is anyway unit length, so this can come out. So the double gradient of this displacement in Z function is going to play a role. Second component, similarly by the same reasoning, can be said to be del square W. So del square W by del Y square, and delta X delta Y is again the normal. Both of these have to together resist the load Q delta X delta Y, because these are summation of the force. So the equilibrium equation will tell you that these are the projected components in this, because in this direction n cos theta on both sides is what the equilibrium force is. The only force which is perpendicular is this angle, right? Sine of this theta. But when theta is small, sine theta is approximately theta, correct? So what we have done is we have taken the vertical projections of loads from here which oppose this load which is trying to bulge this membrane from bottom, the components of the force which are projecting in this direction, similarly component of force projecting from this direction, all the four sides. By warping or by going up as a membrane, these components are produced as a normal reaction when the membrane is glued and attached. And this W is itself like a warping. And this was the powerful analogy of Prandtl, when he said, imagine a membrane which is uniformly loaded, the distribution is such that del square W, so let me just change the marker here, del square W is equal to Q by N is the membrane answer, right? And this looks extremely analogous to my Saint-Wimble displacement warping function. So what I have to do is I have to satisfy W is equal to 0 on the edges, because there cannot be any other vertical function. It has to be 0 since the membrane is glued from all the sides. there cannot be displacement, because if it is not glued and free, what would happen is there is no normal reaction. So which means W equal to 0 is a boundary condition at all edges, which is also similar to what we did for Saint-Venant principle. So he said further that W of xy is same as Prandtl's and Saint-Venant's psi of xy. So Q by N is nothing but minus F, which is nothing but 2g d theta by dz. So he said it is equivalent to a torque. What a membrane sees as load by normal reaction is nothing but that force, the constant, which is 2g theta dash. So you can use this to solve your problems. And this was one of the beautiful analogy which has helped the world. Second, we looked at this. Torque is nothing but 2 times psi. Right? He said here, similarly, the volume of membrane is nothing but W dx dy. That's the volume it will occupy, because W is what it is going to go up as a bulge rather than a plain sheet now. So what he said is, if you compare these two, the torque equivalent, the couple you are applying is nothing but volume of membrane. So you have transformed a first set of problem into completely different physics of second problem, which are mathematically superimposable. This is much easier to handle, right? Because unit loads Q by N are very easy to handle without looking at any other complexity. So you have transformed your physics problem into a mathematics which is repeatable in other physics in same consistent solution, and you can transpose back W as psi and solve your torsion problem. So that was the membrane analogy, a very powerful analogy by Prandtl. The third section, therefore, as we said, is now of thin rectangular plates. Right? They have this length, which is S by 2, S by 2, thickness is T. Right? Now, if this is the cross section, imagine this is to be a cross section. There is going to be this twist, and then there is this going to be warping, which is going to come out. What we have said is, if you see carefully, since boundary conditions will tell you that they have to satisfy no force, no shear and no strain conditions, the functions which will look for stress or strain will be something like this parabol, right? Maximum here, like a membrane. Now look at this as a membrane. Membrane analogy gives you external good handle on physics. So it is like this membrane, which is going to expand and collapse, and expansion is maximum here, like a warping function. In narrow plates, the biggest advantage is because they are assumed to be thin, so T is less than S. Why? Why? Your aircraft structures would be slender structures. From analysis point of view of torsion, it is extremely fair to assume this. S by T greater than 10 is typically where we deploy these methods, which is reasonably true in our aircraft. So we are interested in choosing this. Here, since variation along X is negligible, because see, you have to compare these two profiles, right? A function which goes from 0 to 50 over a length of 100, and function which goes from 0 to 20 over a length of 5. This is very, very smooth and gradual compared to this. So which means from analogy or physics point of view, what we are saying is the stress function is going to be simply invariant of y, the S, right? Only the X variation is what we are interested in. My problem becomes as simple as this: d square phi by dx square, because y variation of phi. So phi is approximately function of x, because g of y variation is negligible. That's the first assumption of thin sheets. Then if you integrate this, since this is constant, phi is going to be minus g d theta by dz x square plus bx plus c. We have to now find b and c such that the boundary conditions can be found. Now phi is equal to 0 at t by 2, plus or minus. If I substitute this, right, then minus g d theta by dz t square upon 4 plus bt by 2 plus c equal to 0. Right? Two unknowns, two equations can be added. If I add them, 2c is equal to g d theta by dz t square upon 2. This is going to give me t square upon 2 going on the right side. So c is going to be simply this, right? And if I have c as this, which is getting added, b has to be 0, which means there is only square variation plus a constant. And we expected this, right? Any linear variation with x, by changing simply the frame of coordinate, you will have a problem because it will have x minus L, the constant error building. So even from mathematical induction, see how I am reasoning this. Even from mathematical induction, any x variation which is only an odd polynomial, 0, so 1, 3, 5, cubic splines, cannot tolerate such functions because they can never be harmonic. Simply by changing the frame of coordinate, you will have problems. So all square and constants or fourth order, the even series powers will sustain this because they are independent. See, plus and minus, the changing of signs become a problem. So mathematical reasoning could have also told us, but we have simply just simplified the problem and derived it on our own, right? So if this is the case, what we are saying is this can be simply written as therefore phi is equal to minus g d theta by dz x square minus t by 2 whole square. So that when x becomes t by 2, phi becomes 0, otherwise it follows this parabolic profile. Now we are also clear why it is not shaped like this. It cannot have a gradient like this, therefore it has to be smooth, and since it is second order, it is parabolic. So in the thin strips, the formation of a problem has given us to this value. Now, once we know the phi, we have to know tau zx. Right? Tau zx is going to be 0. Why? Del phi by del y, gone. And tau, so which means the stress in this plane of the slab, right? This is how the slab is going to look like. The stress in these directions is 0. Only stress that you will see are these, right? So this is another important analogy. Because the y dimension became irrelevant or negligible in the variation, this became 0. So only one dimensional planar stresses, tau zy. This is what? G d theta by dz, right? And 2 times, so x, because it is minus of this, so this is my tau zy, which means tau zy max is 2g, so gt theta dash, this is simply theta dash, and minimum is minus gt theta dash, and it is 0 at x equal to 0, right? So it is this variation. It follows this linearity, right? This is also clear. From warping also we are clear, it has to go from negative to positive, right? In warping, when the bulge was W, N becomes something like this. That's how it holds, right? The projection component. So again, the membrane analogy is helping us to correlate back and validate from physics point of view intuitively whether this is right. So this is clear. So tau zy is now clear. Now let us look at this torque equation, phi dx dy, double integral, right? If we look at the double integral, what I am going to get is g d theta by dz is going to come out, right? And this is gj d theta by dz. See, my whole objective is to find the inertia, moment of inertia, the rotational inertia, right? G. for this thin section, because that is my structure's property. Based on MOC, the material of construction, and based on the dimensions, I can find this, and then have different torque loading conditions to find out what is twist and what is happening. Right? So this is going to come out. dy is invariant, so y is going to go from minus s by 2 to s by 2. So s is going to be here, right? The length, because dy. So dy goes from minus s by 2 to plus s by 2. So s has come out anyway, I know. So x square integral is going to be x cube by 3 from minus t by 2 to plus t by 2. I am keeping minus sign here, right? So t cube by 8. So t cube by 4 this will be, because both will get added, a minus b minus a minus b. So t cube by 12, right? So this will become minus of s t cube by 12, right? This constant term is not yet gone. It is plus s t square upon 4 into t by 2, right? Because one x is going to come, which t by 2 minus t by 2 is going to give me t. So t cube by 4. So this can be 3t cube by 12. So finally, the j that you will arrive at is nothing but s t cube by 3. Very, very important analogy. So the rotational inertia is approximately s t cube upon 3. And we have said s by t greater than 10, this holds very, very true. In reality, in aerospace, when you start building this first approximation, Prandtl immediately suggested himself a correction factor mu. Because when the ratios are in excess of 10, error is only about, so if this is about 10, error is 6%. When they become slightly smaller, they use this. So this is reference value. So for different s by t, he gave these correction factors for inertia, so that experimental values will start matching. So we have defined phi, we know the stress variation, we know the inertia. Now we have to find out warping function, right? How will you find a warping function? To find out the warping function, you need to go back to your definition of gamma, right? Tau zx is 0, which means gamma zx, which is del w by del x plus del u by del z is 0. Del u by del z anyway is 0, so del w by del x, right, is what I am interested in. Now, what is del w by del z? U was minus theta y. So this is minus of d theta by dz into y. So this becomes y into d theta by dz, right? So I get w as x y d theta by dz plus constant. I can simply integrate, there is no x function here. So warping function is something like this. Now at origin, when x and y are 0, w has to be 0 because it is doubly symmetric. Otherwise there will be an offset. There cannot be any warp at the center line. Had been a warp in a membrane, you could have seen a bulge which is floating out. So my warping function w is xy d theta by dz. See how everything has solved. U function is known, v function is theta x. So I know all the three displacement. Now to note gj theta dash is equal to torque. For a given torque, I also know d theta by dz. Gst cube, right? So moment I substitute these known constants of my structure and loading condition, I know the rate of twist. I know warping. I immediately know based on this the components of u and v, right? So see, I've solved this entire problem of thin sheet. And this was the third section of this property of why thin sheets are important. Thin sheets, therefore, we said that for S by T, Prandtl gave us this beautiful analogy and outcomes, and he gave the correction factors. So the entire problem is very easily solvable, and thin sheets are particularly important in our aerospace analysis, because of which this Saint-Venant's warping function and membrane come together to give me this solution. This ends our entire theoretical analysis and basis physics and mathematical foundations of torsion as a chapter. We are closing chapter 2 from a theoretical, mathematical and physics point of view. We will now look at tutorial 2.2, where we will solve some questions on this torsion and close this chapter, and then move to chapter 3, which is about bending and buckling. Thank you.